If you're tackling advanced calculus, you know that partial differential equations, or PDEs, can be a real beast. But what if I told you there's an incredibly elegant shortcut for a huge class of them? Okay, let's dive right into one of the most powerful techniques in your toolbox: separation of variables.
I mean, this is the central challenge of a PDE, right? You've got a function that depends on multiple things, say space and time, and they are all tangled up, all changing and interacting at the same time. It's kind of like trying to describe a ripple in a pond, where every single point on the surface is moving up and down at every single moment. It's a lot.
Let's look at the classic heat equation. On the left side, you have U sub T, which is how fast the temperature is changing over time. And on the right, you have U sub X, which describes the curvature of the temperature in space. See how they're completely mixed together in one equation? Time and space are locked in a dance. So how in the world do you start to pull them apart?
Well, the breakthrough comes from a surprisingly simple but absolutely brilliant idea. Instead of just trying to brute force the complexity, we're going to make a really clever assumption about what the solution looks like. This is the secret.
And here it is. This is the core idea. We just assume that our complicated two-variable function, u of xt, can be written as the product of two much simpler functions: a function x that only depends on space, x, and a function t that only depends on time, t. That's it. That's the entire foundation of this method.
This quote just perfectly captures the intuition here. Think about it. Imagine you have a temperature profile along a hot metal rod. That's your x of x. Our assumption means the shape of that profile doesn't change. It just gets scaled up or down over time by that t of t function. It's like a single shape that just fades away as the rod cools.
Okay, so how do we actually put this assumption to work? Well, it turns into a very straightforward, almost mechanical, 5-step recipe. If you just follow these steps, you can take a ridiculously hard PDE and turn it into something way more manageable.
So it all starts with our big assumption. We plug that form into the PDE, we do a little bit of algebra, and then comes the magic step. We shuffle all the terms around. Then we introduce something called the separation constant, and voila, we are left with two much simpler equations to solve.
And this is the whole point of that algebraic game in steps 2 and 3. Your entire goal is to get to this beautiful moment where one side of the equation only has x's in it and the other side only has t's. And think about that for a second. How can a function of only x be equal to a function of only t for every possible value? The only way that works is if they are both equal to the same constant value.
All right, enough theory. Let's see this recipe in action. We're going to use two of the most famous PDEs out there, starting, of course, with the heat equation.
So we start with our heat equation. When we substitute u equals x times t, remember how derivatives work. The time derivative only sees the t function, so we get t prime. And the two space derivatives, they only see the x function, giving us x double prime. Look at that, it's already starting to look simpler.
And here's the magic move. We just divide the whole equation by k times x times t. And look what happens. The left side is purely a function of time, and the right side is purely a function of space. We did it! We successfully untangled them.
Now, since both sides have to equal that constant, which we'll call negative lambda, we can split that one equation into these two. And what are these? These are ordinary differential equations, or ODEs. If you've taken a first course in Diff E, these should look super familiar, and more importantly, you know how to solve them.
Okay, let's run that play again, but this time with the wave equation. This is the one that describes things like a vibrating guitar string. Notice the big difference here is a second derivative in time, UTT, but the process is the same. We plug in u equals xt, and the derivatives only act on their own functions. So we do the separation, set both sides to our constant, and again we get two ODEs. Now check this out. The spatial equation, the x part, it's identical to the one from the heat equation. But look at the time equation. It's got a second derivative, t double prime. That small change is everything. It's what leads to oscillating, wave-like solutions instead of the simple decay we saw with heat. The physics is literally baked right into the math. It's just so cool.
So after all that, what is the grand payoff? Why is this method so incredibly fundamental? Well, it all boils down to a really simple but powerful transformation.
This entire process takes one
Seemingly impossibly complex problem
and turns it into two
Much simpler problems that you already know how to solve. You're literally turning a hard problem from an advanced course into two easier problems from your intro ODE class.
That right there is the awesome power of this technique.
And this really leaves us with a final thought, doesn't it? This mathematical trick is actually a profound problem-solving principle. It teaches us that sometimes the key to cracking an overwhelmingly complex and interconnected problem is just finding the right perspective, the right assumption that lets you break it down into smaller, independent pieces you can actually get your hands on and solve.